For this lesson, we're going to talk about something called linear programming, and we're going to use the graphical method. So this is not the type of programming as in computer programming. This is a way to solve equations or solve application problems. And the goal is to find some optimal value while you are subject to various constraints. So this is very similar to having inequalities, systems of inequalities like we talked about in the previous lesson. Your constraints could be things such as transportation, time, money could be a constraint, and a whole list of things. So the functions you're optimizing are called objective functions. You have some objective you're trying to satisfy, and that is the main function of your problem. So I'll just jump into example number 1. We're going to find the maximum and minimum values of the objective function Our objective function will always be a z function. So in this case, z equals 2x plus 5y when subjected to these constraints. (3x plus 2y must be less than or equal to 6. X plus y must be greater than or equal to 1. Negative 2x plus 4y must be less than or equal to 8. And x must be greater than or equal to 0, as well as y must be greater than or equal to 0. So we're dealing only with positive numbers, and each of these constraints or inequalities must be met. So the process that you want to follow to solve this way, first is to solve for y. Any of your constraints that are not solved for y. So I'm going to copy each of them down and solve for y. There's this one. I'm going to subtract 3x and divide by 2. And then the negative 2x plus 4y is less than or equal to 8. Adding 2x and dividing by 4. And then lastly, the x plus y must be greater than or equal to 1. I just need to subtract x over. Once you have solved all of your constraints for y, your second step is to graph. We're graphing just like we did in the previous lesson. And keeping in mind that x and y must both be positive, I'm mostly going to just graph in the first quadrant. So I'll show a little bit of the other quadrants, but I'm going to focus on the first quadrant for my graph. Okay, so this one has a y-intercept of 3 and a slope of negative 3 over 2. So down 3 and over 2 would be right here. Graph that inequality. And it must be less than . And then the next one here has a y-intercept of 2 the slope of 1/2, so up 1 and over 2. This is also a less than, so I'm going to shade below this one. And then the last one over there has a y-intercept of 1 and a slope of -1. And that must be greater than or equal to. And then the other two constraints, x is greater than 0 and y is greater than or equal to 0, are pretty much satisfied already just by the way that this is drawn. But that means I have the x-axis and y-axis and the x-axis and greater than that. So the region that is shaded by all 5 inequalities is this shape here. And then the question that we're asking ourselves is, when is Z maximized? So we have to pick an ordered pair from that feasible region. Anything that falls within this region, we can plug into and find our Z value. So we could try something like 1, 1. So if I plug that into my Z function, which looking up on your paper would be 2 times X, or 2 times 1 plus 5 times Y, so 5 times 1, and that's 7. That just gives me a random value of Z. Do I know if that's the maximum or not? Not exactly. So the maximum is going to be at an intersection. And I'll show you how we determine this on our next example. But in this case, we're going to be at the intersection of y equals 1/2 x plus 2. That's the one I have in purple here. And y equals -3/2 x plus 3, which is this green graph right here. If I set those two equations that are equal to y, set their right sides equal to each other, I can figure out the x value where the maximum occurs. So if I add the 3/2 x to the left, I'd have 2x equals, and subtracting 2, that's 1. So x equals 1/2 is going to provide the maximum Z value. And then I can use either of these equations to figure out the corresponding Y value. So let's say we use Y equals the 1/2 times X, which we now know is 1/2 plus 2, and 1/4 plus 2 is 9/4. So then our Z value is 2 times 1/2 plus 5 times 9/4, which comes out to be 12.25. So you could do that by guessing and checking, but as I said, in a minute, we'll talk about how to find those exact values. So this particular problem has a maximum value of 12.25 at the ordered pair 1/2 and 9/4. The minimum value is at the ordered pair 1, 0. So if I plug that into Z, That value is 2. And now I have both the maximum and the minimum that were asked for. So basically we can graph and know that we can just randomly pick points in our shaded region, in our feasible region, and figure out what gives us the biggest or the smallest values. But it's not very likely that you would choose this particular ordered pair by guessing and checking. So we use something called corner points. So a corner point is a point in the feasible region where the boundary lines of two constraints cross. In the feasible region is bounded. It's a new vocabulary word, bounded, meaning it has boundaries. If it is enclosed completely by our boundary lines. So in the example we just finished, we have a bounded region because if you were inside of this region, there's no way that you could get out and escape without crossing one of our boundary lines. If that's not true, then your region is unbounded. So the feasible region is unbounded if the boundary lines do not completely enclose the region. So we need those definitions to be able to interpret what we're going to use, which is called the corner point theorem. The corner point theorem has two cases. Case number 1 says if the feasible region is bounded, then the objective function has both a maximum and minimum value. Each occurring at one or more corner points. Case number 2 for when the region is unbounded. The feasible region is unbounded. Then the objective function may or may not have a maximum and a minimum. If one exists, then it will occur at one or more corner points. So let's use this theorem to solve linear programming graphically. So your first step will be to write the objective function and all constraints. So if you're working from a word problem, you'll have to determine what those are. For this example, we're going to use the objective z equals 5x plus 2y. And we will be subject to the constraints 3y minus 2x must be greater than or equal to 0. Y plus 8x must be less than or equal to 52. Y minus 2x must be less than or equal to 2, and x must be greater than or equal to 3. So after you have your inequalities written, you will graph the feasible region. So graph that as a system of inequalities. So I'm going to take each one and solve for y first. Y is greater than or equal to 2/3 x is the first one. Y is less than or equal to negative 8x plus 52 is next. Y is less than or equal to 2x plus 2, and then x is greater than or equal to 3 is already in good form. So if x is going to be greater than or equal to 3, I know I don't need any negative x values. So again, I'm going to focus my graph on the first quadrant. Okay, so my first one is 2/3 x. So that goes through the origin. And I'm going to go up 2 and over 3. And graph that inequality. Shading above. Actually, I'm going to hold off on my shading until I get them all drawn. I'm going to label them so I can remember which is which. Okay, the next one has a y-intercept of 52 and a slope of negative 8x. So I'm going to do a sketch here. I put this into my calculator and figured out that the x-intercept of that particular graph is at a little bit bigger than 6. So 1, 2, 3, 4, 5, 6, 7. So I'm going to have it cross here. And I'm just going to draw a very steep line because negative 8x slope is pretty steep. And then 2x plus 2. So a y-intercept of 2 and a slope of 2. So up 2 and over 1. This line. And you would shade below both of the last two that I just graphed. And then x has to be greater than or equal to 3. So draw that vertical line at 3. And greater than or equal to would be to the right. So we're going to go greater than this, less than, and greater than. So our feasible region is this quadrilateral right here. So what I need to focus on are the values of these corner points. And to figure out your corner points, that's our next step. You set the inequalities equal to each other where they cross. So the 2/3 x line, y equals 2/3 x, crosses x equals 3 at some point. So I'm going to set those two equal to each other. And if I multiply by the reciprocal, that would give me a value of 2. Sorry, back up a second. I did that wrong. This is an x value. X does equal 3. So I'm looking for where y equals 2/3 x crosses x equals 3. So if I plug 3 into that, 2/3 times 3 is equal to 2. So I get an x value of 3 and a y value at 2 right here where those two cross. The next intersection I'm going to look at is right here. That's my 2/3 x line. And negative 8x plus 52. So setting those two equal, because I don't have an x or a y value on this one. If I add the 8x over, that'd be 26 over 3x equals 52. Multiply by the reciprocal gives you an x value of 6. You can plug 6 into either of these equations. I'm going to plug it in here. 6 times 2/3 would be 4. So that would be a y value of 4. So 6, 4 are the coordinates of this point. And then I'm going to move up here to where x equals 3 crosses this line, which is 2x plus 2. So again, I know my x value, so plug that in. That would be 8. So that would be the 0.38. And then lastly, where y equals 2x plus 2 crosses negative 8x plus 52. So setting those two equal, be 10x equals 50, or x equals 5. If you plug 5 into either equation, I'm going to go here. 2 times 5 is 10, plus 2 is 12. So that'd be a y value of 12. That means this ordered pair of the intersection is 5, 12. So now we simply take each of those values and calculate the objective value at each corner point. So the corner points were 3, 2, 6, 4, 3, 8, and 5, 12. The objective value is z. Z is 5 times the x plus 2 times the y. So the first one would be 19. Second one would be 38. Third one gives me 49. And the last one, oops, I did that wrong. $31. The last one gives me 49. So since our region is bounded, we have both a maximum and a minimum. They both occur at the corner points. So we can just look at this list and find the smallest value, and that is our minimum, and the largest value is our maximum. So then we can conclude that the minimum value is 19 at the ordered pair 3, 2. And the maximum value is 49 at the ordered pair 5, 12. So for example number 2, we want to minimize the objective function x plus 2y subject to the constraints x plus y must be less than or equal to 10. Solving that for y would be y is less than or equal to negative x plus 10. And then 3x plus 2y is greater than or equal to 6. That solved for y would be y is greater than or equal to negative 3 over 2x plus 3. X is greater than or equal to 0. Y is greater than or equal to 0. So again, here our graph will focus just on the first quadrant. So I'm going to draw a first quadrant graph. My highest y-intercept is 10, so I'm going to number this will be 10 up here. So that graph will start at 10 with a slope of -1. There's that first one, and we'll shade at the end, just like last time. Second constraint has a y-intercept of 3, slope of -3 and over 2. That puts it down here at the bottom. So thinking about shading, just kind of as we go for this line, we'll shade below for less than and this one up. So right now we're in between these two. And then x and y both have to be greater than or equal to 0. So that completely encloses our area. Our feasible region is this quadrilateral here in the middle. So this one actually ends up being fairly easy to figure out our corner points. This corner point and this corner point, 3 of them are intercepts that we already have. One of them is 0, 3. One of them is 0, 10. The other one is 2, 0. And then for this top graph, the first one I graphed, that has a slope of -1. It's also going to intersect the x-axis at 10. So that point would be 10, 0. So taking each of those ordered pairs and plugging into our z, our objective function, I have 0 plus 2 times 3, that's 6. 0 plus 2 times 10 is 20. 2 plus 2 times 0 is 2. And 10 plus 2 times 0 is 10. So in this particular problem, we were just asked to minimize. So we just need to identify the lowest of those values. And we can conclude that the minimum value of z is 2 at the ordered pair 2, 0. And last example here, number 3. We're again going to minimize an objective function 2x plus 4y subject to x plus 2y is greater than or equal to 10. 3x plus y is greater than or equal to 10. And x and y are both greater than or equal to 0. So if I solve these for y, I would have y is greater than or equal to -1/2 x plus 5. Y is greater than or equal to -3x plus 10. And then this restricts me to the first quadrant again. So drawing a first quadrant graph. Highest y-intercept is 10. here. Okay, my first inequality has a y-intercept of 5. 1, 2, 3, 4, 5. Okay, with a slope of -1/2. So from this y-intercept down 1 and over 2. And again, down 1 and over 2. This line. And for that graph, I would shade above. And then the second one has a y-intercept of 10, the slope of -3, so down 3 and over 1. And that would also be shaded above. So then we have the restriction that x and y must both be greater than 0. So that stops our feasible region here on these two parts. And so it's this first quadrant region that's above both of those inequalities. So all of this out here. So this is the first example we've seen of an unbounded region. There are boundaries on some of the sides, but there's a big open side over here. So from the slopes and the points that we used, we can tell that this intersection would be 2, 4. The other points that we need to call our corner points are where the other intersections occur. So we have 2, 4 as one of our corner points. We have 0, 10. And then this line, if I started it at 5 and I go down 1 and over 2 and do that until I intersect the x-axis, this will intersect the x-axis at 10. So that corner point is 10, 0. So again, we'll substitute those into our objective function. So 2 times 2 plus 4 times 4, that's 20. 2 times 0 plus 4 times 10 is a value of 40. 2 times 10 plus 4 times 0 is a value of 20. So we're looking for a minimum, and we actually end up with 2 of the same value, and they're both the lowest value. So we would say that the minimum value of z is 20 at both points, 2, 4 and 10, 0. And just as a note, this value will also be achieved at infinitely many points between the stated points along the boundary line.